In this lesson, we shall look at course 1501 Theoretical Computer Science. So we start by looking at question 3.1 from the paper we're looking at since yesterday. We let the set A contain the elements 1, B, and C. The set B contain the elements 2A and C. And let T contain those particular ordered pairs. And this set T, let it be a relation from B to A. Now, let us determine the set composition. Let us determine the set composition. So determine, therefore, the set composition will then proceed as follows. Right, so it would therefore be containing elements of the following form. So the set composition of T with T would therefore contain C and 1. Right, it contains C and 1, given that T is that. Perhaps a couple of things we need to first look at. Let us first list the elements in T. And they are C and 1, C and C, A and B, 2 and 1, 2 and C. Those are the elements in the set T, and therefore, when we perform a set composition, we shall therefore find the following elements. Right, so the elements in the set composition of T with itself would therefore become the following. Right, so it would be C and 1, C with C, 2 and 1, and also 2 with C. And because it is a composition of the set C with itself, so that is what we're able to achieve there. Which ordered pair should be deleted from T to make it an irreflexive relation? Right, to make it an irreflexive relation, we need to remove the element that allows C to be related to itself, and we need to remove C and C. So this one should be removed. Should be removed. Next, we'll look at 3.2. Right, let A contain the elements 1 and 2, B contain the elements 2A and B. Give an example of an injective function from A to B. We need to give an example of an injective function from A to B. To start with, we take note of the fact that indeed the set A contains 1 and 2. B contains 2A and B. F, being a set from A to B, would actually be containing the following, because let's just give an example of an injective function. So let's take a look at this one. If we map 1 to 2, right, we map 1 to 2, but we also map 2 to A. We map 1 to 2 and you map 2 to A. So this will be an example of an injective function. And an injective function is to do with what we call a one-to-one function. And a one-to-one function would actually therefore map different elements to different images, at least. Next, we let A contain the elements 1, 2, A and B. B contain the elements 2, 3, and C. C contain the elements 3A and D. For each of the following functions, write down whether it is injective, bijective, surjective there. Right, you do not have to prove anything. Okay, this is it. We do not have to prove anything. But now the function, there's a function m from C to B is defined by that particular set. So the functions can be defined as equations. They can also be defined as sets. Right, so this is what we have. For each of the following functions, write down whether it is injective, bijective, or that. Injective is one-to-one. Bijective is obviously both one-to-one and onto. There's an onto function. We shall describe that, but a function is onto if only you have two sets, x and y, and you can take a set y, such as for every element y here, right, for every element y, you can always get an x that is mapped onto that by a relation we can call f that maps the two sets. At this point, we are then saying, okay, so your so a surjective function is also called an onto function. Okay, it's also called a surjection. A surjection. Right, it's also called a surjection. You do not have to prove anything. All right, so looking at the function from C to B, defined by M. Right, is it injective or not? Right, we can see that this function is actually a bijective function. Let us take a look and understand why. Right, we understand and we see, therefore, that this function here is bijective. Right, because one thing we can see with these particular sets, different elements, like there's 3, D, and A. So the domain elements are all different. And so the images are also different. In other words, what we're having here is the following. Obviously, we have the set M. We have the 2, 3, C. Right. I want us to list the elements in X first. And it's going to be 3DA. Right. It's going to be 3DA. 3 to C. So 3 goes to 3. We can see D goes to 2 and by dint of this. Okay, this relation is said to be a one-to-one relation, so what you call an injective relation, because every element is mapped to onto itself, or onto a different element, or different elements go to different images, and also this function is onto, right? Because for every element that is there, in the image set or in the range, you find domain elements that are mapped onto this. So we don't have elements that are roaming around there. So it is certainly onto, or it is certainly a surjective relation. Right, but because it is both one-to-one and onto, we say it is 2 times that. So we say it is bijective, where bi means 2. Look at the next question. Now, give an example of an injective function from A to B. Obviously, we have certainly given that, and we looked at that. We move on. Let A contain the elements 1, 2, A, and B. B contain 2, 3, and C. C contain 3, A, and D. For each of the following functions, write down whether it is injective, bijective, or surjective. You do not have to prove anything. Right, so dealing with the function from A to C, defined by n equals that. Right, defined by n equals that. Okay. For each of the following functions, write down whether it is injective, bijective, or surjective. You do not have to prove anything. Let us look at this function here. There's a function that is mapped from A to C, but the examiner is clear that don't prove anything. Do not prove anything. But here, you just need to state the property of this particular function here. And let us look at this together. But this function is clearly a surjective function. We shall explain why it is surjective. Because if you look at the fact that A is that, B is that, and C is that, and then if you look at these here, B1, A, and 2 are all different. So at this pointer, we have a set X and we have a set Y. B1, A, and 2 are all different. D, A, 3, and D. D is occurring twice. So you can just put it once. And therefore, let us map this. So B goes to D. Like so. And then we have 1 goes to A. Like so. A goes to 3. Exactly like so. 2 goes to D. Two things. So B and D, B and 2 both go to D. They both go to D. So the question then is, what is the point of this? What is the point of this? Well, what is the property of this function? Well, we're able to see that at this pointer, this function here is a surjective function. For every element here, we can get an X that is mapped onto it. There's no element that has no friend from the X set, from the domain set. And so now we actually are able to see, therefore, this function itself is surjective. It's actually exactly a surjective function there. Now move on. Roman figure 3, there's a function, there's a map from B to A defined by this. So you have X and then Y. That is F 2C3. 2C3. 1BA. 2 goes to 1. C to B. Right, 1BA. Clearly this function, because it's for every one element, it goes to one image. One element is one image. One element has one image. So this one is clearly what you call an injective function. It is very much injective, okay? Very much injective. Very much injective. Very much injective. Let's look at the next question. Question 3.3. Let R be a relation on Z. Right, we're looking at Z relations at the moment. Let R be a relation on Z defined by XY in the relation. On this actually be the case if and only if Y is minus X plus 4. Prove that R is symmetric. Prove that R is symmetric. Okay, now it's easy. It's very, very easy. Let us ponder to reason this out. And look at how best we can manage this particular question here. Moving forward. 3.3a. Right. Prove that R is symmetric. Well, we remember that a symmetric property is the following property. Now, we note that for R, right, for R to be symmetric, y equals minus x plus 4 must equal x minus y plus 4. Right. And so this would mean y plus x, if you move the y to the other side, the result is 4, which is true indeed, right? And with these mentioned, actually, it has the implications about the fact that, therefore, our x is minus y plus 4. This would mean, therefore, x and y and x are elements the relation, elements of the relation R, the elements of R, the relation. That is symmetric. That is symmetric. That is symmetric. So note, therefore, that this would be symmetric because of this particular relation. Because of this particular relation here. Right. And because of the elaborations given, we're able to see that whenever xy is an element of R, because symmetric means xy xy is an element of R, okay, or we then say, we put it like so, to put it better, or nicely at least, if xy is an element of R, then yx is an element of R. Then yx is an element of R. And by dint of this is true for relations that are symmetric. This is true for relations that are symmetric. We'll move on to the next question. We move on to the next question. Let f and g be functions on the positive integers, z plus defined by xy being an element of the relation f, if and only if y is equal to 3x plus 2, and xy be an element of g, if and only if you have the cube of x plus 1. Determine the composition of the functions there. Determine the composition of the functions there. Right, and to determine the composition of the functions, we proceed as follows. So the composition of these functions is going to be f g like this. And f is 3 times the argument, x. So it's going to be f is 3 times g. Right, plus 2. The g is x cubed plus 1. Three x cubed plus 5. So this is 3x cubed plus 5. 3x cubed plus 5. Next question. Prove that function f is injective by using the definition of injectivity. Second Roman figure. Prove that the function, so now we need to present a proof. Now to prove this, we note that for all A and for all B, right, we note that for all A but also for all B, we have exactly the following. Okay, for all A and for all B, A not equal to B means that f of A is not equal to f of B. Alternatively, you can say for all A, for all B, f of A equals f of B. This means that A equals B, and this is the definition of injectivity. A not equal to B means f of A is not equal to f of B. For all A, for all B, f of A equal to f of B implies that A equals B. Okay, so we are saying these are the two cases of injectivity. Either you, to show that a function is injective, you start with A not equal to B, and you must prove that the images are not equal as well. That is f of A is not equal to f of B. If you start with the images, you equate them. You make them equal to each other. And then say, okay, for all A, for all B, f of A equals f of B. You assume f of A equals f of B. Deduce and prove that A equals B, of course. So now, since in this case, since f of x, of course we know that this is 3x plus 2. What it does, it produces a unique value. A unique value for every unique input f of A equals f of B. Right, only when Only when A equals B, we can therefore conclude without any fear of contradiction that F itself is injective. Let's just reason about this proof a little bit for just a minute. Okay, we need to prove that F is injective by using the definition of injectivity. What is the definition of injectivity? Right, the definition of injectivity is the definition given here. So it comes twofold. Either we say for all A, for all B, we assume that A is not equal to B and deduce that f of A is not equal to f of B. For all A, for all B, we assume that f of A equals f of B and deduce that A equals B. So we are spoiled for choice. We can do any of this, but we decided to go with the second one, to say since f of x equals to 3x plus 2 produces a unique element for every unique input. We started with f of A equals f of B. This is it. We began with f of A equals f of B. With that, then, this is true only when A equals B, and this means injectivity, yeah? Alternatively, a student can start as follows and say, right, we can say alternatively. Alternatively, f of A equals f of B, 3A plus 2. So, of course, our f of x is 3x plus 2. So you can put 3a plus 2 in the place of b. You can put 3b plus 2. And this means that we have 3a equals 3b. Divide by 3 and you get that a equals b. So obviously we started off with f of a equals f of b. And this implies that, this implies that, this implies that. So f of a equals f of b implies that a equals b, and therefore f is injective. So this would be one way of dealing with injectivity. This will be one way to deal with injectivity as we try and explore the course in detail. Right, let's move to the next question. We are practicing and we're looking at past examination questions and trying to make sure we make the most of this course, but we understand, most importantly, the underlying notions here that underpin this exciting course. Let f and g be two functions on positive integers z plus. And so now they are defined by xy, and in f, xy is an element of f, when if and only if y is 3x plus 2, xy is an element of g if and only if y is x cubed plus 1. Now function g is not injective. It's not surjective, excuse. Function g is not surjective. Give a counterexample to prove it. This is it, to prove it. So function g is not surjective. Give a counterexample. Going to discuss what we call a counterexample to prove it. Show how you get your answer. The marks are 2. So there are two things here. Obviously, there are two things here. Counterexample and also showing how we get our answer. Let us look at this together. Right, let us look at this together. We start by saying since G is not surjective, on the positive integers, there exists Right, there exists. This is the proof. There exists an element in the codomain. In the codomain, not in the range. Not in the range. We note that for all A, for all B, or rather for all A, is what we say. There exists B, or let's start as follows. Let's say for all B. Yeah, you can start like that. For all B, we can get A. For all B, there exists A with f of A not equal to B. Now, what we're able to see here, whenever we define the range of G, well, the range of G is Y, which is x cubed plus 1. Which is the same as we can transpose the terms, getting x cubed equals y minus 1, which is the cube root of y minus 1 which means the range of G contains y such that x is the cube root of y minus 1, x element of z plus, and therefore, in this case, it would therefore mean, that x is the cube root of b minus 1 right, and if we take b to be 0, so that we have 0 minus 1, this will be the cube root of minus 1. If this is the cube root of minus 1, if you cube both sides, of course, it doesn't matter. The cube root of minus 1 is minus 1. Okay, so we put this aside. We are still doing a Roman figure 3. Since x is an element of z plus x is an element of positive integers, this is not possible. This is not possible. Therefore, G is not surjective. G is not surjective. G is not surjective. Let us reason this out and make sure we sort of understand what is happening here. In Roman figure 3, the question was, function g is not surjective. Give a counterexample to prove it. Show how you get your answer. The marks are 2 there. We started off by saying g is not surjective on z plus, on the positive integers. If this is the case, it means there exists an element in the codomain that is not in the range. What is the meaning of this? We speak about two sets, X and Y. There's something we call the codomain and there's something we call the range. So the codomain sits inside the range, and therefore the codomain is a subset of the range. Is a subset of the range. So the codomain sits inside. But if a function that is, if we assume that since g is not surjective on the positive integers, z plus, there exists an element in the codomain. Yeah, you can find an element in the codomain that is not in the range. I mean, we have the codomain. This is what we're saying here. The codomain is bigger, but the range is smaller. That's what we're saying. The codomain is the largest set of images, but the range is smaller. That's what we're saying here. Since G is not surjective on Z plus, there exists an element in the codomain. So you can get an element in the codomain that is not in the range. Yeah, there's an element here that is like sitting here that is not inside the range. The range is small, generally. So to actually start off the proof, because we need to give a counterexample to prove it, about G, and G is the x cubed plus 1. So now we can give a counterexample, or we can proceed as we've done. So yeah, this is just an example. So we're saying for all B, there exists A. For all B, the B that sits here, the B is sitting in the codomain, but is not in the range, yeah? It's sitting outside the range, but it is there in the set of the images where we have our Y values. So for all the B, there exists an A, the A sits here, such that when we map these, this f of A does not go to B. It doesn't. It doesn't. It doesn't go to B. Right. Okay, we are going back. We have that now, because we want to prove it's not surjective, we take a B that is outside the range, but it is in the codomain. And then we're then saying for all the B that are outside there, or that are in Y, there exists an A that is not mapped onto this. The range of G contains what? It contains Y. And this Y is x cubed plus 1, yeah, because Y is x cubed plus 1 for G. We can manipulate and make, for example, x the subject of the equation. And if we manipulate, we transpose the 1, making it negative, so that the x cubed is y minus 1. And x, therefore, becomes the cube root of y minus 1. The range of G, is such that it contains it is exactly y. Of course, the range contains y values, yeah? So it contains y values such that the x is the cube root of y. And we understand we are dealing with positive integers, and therefore now we want to argue that there is an x. There is an x. There exists an a or an x such that it is not equal to its image is not there in the codomain, or it's not in the range, that is. Okay, so we define the range of G like this: to contain the y values such that x is the cube root of y minus 1. So now x would be equal to the cube root of b minus 1. So now if we make b 0, we just choose 0. We have 0 minus 1, which is minus 1. We take the cube root of minus 1. We get x equal to minus 1, yeah? But now we're dealing with positive integers. So x and y must be positive. Yeah, but now we just created a negative on purpose. But to make sure that we can choose a y value so that we have negatives that are coming up. We've seen that there's a negative that has come up, yet we are dealing with a z plus of positive integers. Since x is an element of positive integers, since x is an element of z plus, this is not possible. G is not surjective. G is not surjective. G is not surjective because x is negative 1. So if x is negative 1, since x is an element of positive integers, this is not possible. G is not surjective. So G is not surjective. Then we're done. We're supposed to just give a counter. This is an example, is not a general proof because we took a specific b equals 0. This is it. We took a specific b equals 0. Let's move to the next question as we practice more. Okay, the next question is the ordered pair. Is the ordered pair 2 and 8 in F? Why not? Let us check the ordered pair. F of x is 3x plus 2. F of x is 3x plus 2. So we're getting like f of 2, which is 3 by 2. F of 2. 3 by 2 is 6 plus 2, which is 8. Therefore, 2 and 8, this is an element of f, because whenever x is 2, then y is 8. 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 So yeah, we have proven that 2 and 8 are actually, this ordered pair of 2 and 8 lies in F. Okay, 2 marks there, achieved. Move on to the next one, just practice more. Okay, the next question obviously is about matrices. Consider the following matrices. We're looking at the matrices. This one is called a row vector. Okay, this one, and this one is called the row vector of the size 1 by 2. There's 1 row and 2 columns. This one is 2 rows by 3 columns. 2 rows by 3 columns. 2 rows by 3 columns, yeah? Is it possible to calculate A times B? Is it possible to calculate A times B? Let's check it out. Okay, so now we want to calculate A times B, like AB. So we're going to have A here, and then B is 1, 2, 5, 3, 4, 6. So we continue. We do row by column multiplication, so we have 2 times 1. Right, so we'd have 2 times 1 plus 3 times 3. 2 times 2 plus 2 times 2 plus 3 times 4. 2 times 5 plus 3 times 6. 2 times 1 plus 3 times 3. 2 times 2 plus 3 times 4. 2 times 5 plus 3 times 6. What is 2 plus, okay, 3 by 3, it's a 9 plus 2, it's exactly 11. Next, we have 2 times 2, which is 4 plus 12. Right. So when you multiply this, you know that you're multiplying a 1 by 2, 1 row by 2 columns with a 2 by 3, and therefore you'll get a 1 by 3. So yeah, there was just a repetition there. There was just a repetition, so we only have the top. We only have the top row. Right, we multiply, so this is enough. Right, because when you're multiplying a 1 row by 2 columns matrix with the 2 rows by 3 columns matrix, we then are getting exactly the following. So you have 9 plus 2, which is exactly 11. 12 plus 4, which is 16. 2 by 5, it's 10 plus 18, which is 28. 28. So this becomes the answer. This becomes the answer. So move on to the next question. Let us compute right now this particular matrix difference and product. Well, yeah, scalar multiple of a matrix and the difference of these two matrices. Let us analyze this together. This one we know very well from linear algebra. So we know from MAT 1503. But yeah, we're going to have 2. The matrix A, which is -1, 2, 0. 0 and 3, -2, 3, 1. 0, 1, -2. minus 310. Two by this is minus 240. 026 minus 462. 1 minus 2 minus 310. 2 minus 3 minus 2 minus 0 is a minus 2. 4 minus 1 is a 3. This plus that is a 3. 2 minus 1 is a 1. 6 minus 0 is a 6. 4 minus 2 is a minus 6. 6 minus 2 is a 4. 2 plus 3 is a 5. Okay, let's check this out. Let us check this out. So we have a minus 232,316 minus 645. Minus 645. Minus 645. So this is 2a minus b. 2a minus b. And therefore, this is the result. So in other words, we're effectively then saying the matrix, the scalar multiple, because this one is called the scalar multiple of the matrix A minus 232,316 minus 645. So this would be the 2a minus b as matrices. Right. Now let us deal with the binary operation. Let's deal with binary operations. So now, after having dealt with matrix products and differences and scalar multiples, given the incomplete table below for the binary operation star, complete the table above so that the binary operation star is not commutative. It must be commutative, and that B is the identity element. We note that A star A is B, but we also note that B star B is B. C star C, it's B. So that A star A is B. The question then is, what would A star B be? Right, so this is what we are investigating. So A star B, A star C, right, because we're able to see that there is B right through there. But now A star B would then be what? But so that it is not commutative. Complete the table above so that the binary operation star is not commutative, and that B is the identity element. Yeah? B is the identity element. So if B is the identity, this is the most important thing. So A star B, for instance, is just going to be what? It's going to be A because B is the identity. So you're going to have a C there as well. You're going to have a C there as well. B is the identity, means that B star A is A because B is the identity. B star C because now we have A, B, we're only missing C here. B is the identity element, meaning C star B is C because B is the identity. What is the identity? Identity is the neutral element. is the neutral element. So this is the notion of the identity element that becomes a neutral element there. Okay, let us reason this out. So when you have, for instance, C star A, it's going to be equal to what? Because already here we are dealing with the following. We are dealing with the following. Okay, we've already said that B is the identity. We've already said that B becomes the identity. Right, so that in the end now, this would have to be A. Would have to be A. Because we know that C star B is C, because B is the identity. But for example, let us reason this together. You can say C star, your C star C is B according to this. So, but you also have the C star B. C star B, C. Then we have C star A. Right, we have C star A is equal to what? Right, so if you have, C star A. Okay, there's something I want to deduce here. So you have C star A. Right. Because now if you know that C star C it's B, C star B it's C, it means that you can play around here and put a couple of things you want to put. For instance, in the place of C, what can you put in the place of C? You can put C, which is exactly the same as C star B. And then simultaneously, you already know. So in the place of C, what I'm saying, you can play around with these elements like this. There's more you can explore. What is C? It is C star B. Now you have A. What is A? Right. A, you can see it as, for instance, A star B. Because A star B is A. So you can write A star B. Because that is A. You can play around with the elements like this. And then obviously because this is associative, yeah? So you can associate elements and look at things like B star A. And if B star A it remains A indeed. So you can associate the B and the A. But obviously this is not commutative. So if you have B star A, you get an A. Right, so so if you associate these here, B star A, you get A. Right, and so that will be C star A star B. So now you can look at C star A, or you can look at A star B. And indeed, A star B is A. This gives you C star A still. But if you're going to do C star A, and you agree that C star A should give us A star B, and then A star B would give us exactly a B, which is consistent with this. So now you can then say, for example, C star A, what should C star A give? If then, obviously, look at the fact that we need to complete the table above so that the binary operation star should not be commutative and that B is the identity. As indicated, B being the identity, we're just exploring here, but being the identity means that C star B is just going to be C. But C star C is just going to be B. And therefore, if we reason this out such that it is not commutative, we shall say the following. Okay, look. A star C, it's C. C star A. So C star A is not, right? C star A is not equal to A star C, because that would be commutative there. So this cannot be C exactly, because you complete the table above so that the binary operation is not commutative. If it were commutative, then A star C would be C, but also C star A was going to be the same thing. But it is not the same thing because it is not a commutative binary operation. Okay, just obviously think about this and make sure you can play around with these elements and explore these table much. But yeah, thank you so much for the discussion. It was interesting exploring the binary operations. We shall look more at these in our next discussion. But thanks again, and enjoy your day, and goodbye.